Welcome to all of you. Today we discuss Mathematics Honors Semester 6, University of Calcutta, paper CC14, Numerical Methods, 2021, MCQ. First question is, second degree polynomial passes through these 4 points 0, 5, 2, 7, 4, 17 and 6, 35 is option 1, 2, 3, 4. Correct option is 3 because here column X is first component 0, 2, 4 and 6 and second coordinates fx, and so for x we get 5, 7, 17 and 35, and corresponding first order difference, and 7 minus 5 equals 2 and 17 minus 7 equals to 10, 35 minus 17 18, and the second order difference delta to f is this 10 minus 2 8, 18 minus 10 8. So Newton's forward difference formula gives fx approximately equal to fx0 x minus x0 by factorial 1 into h delta f0 plus x0 x minus x0 x minus x1 factorial 2 h square delta 2 f0. Here h equal to 2 because it is x0 0, x1 2, x2 4 and x3 6. So equidistance nodes. So here h is 2 here, and fx0 here fx0 is 5 and delta f0 is 2 and delta 2 f0 is 8, and putting all these in this formula and we get up to second order difference, this 5x plus x into x minus 2, so we get the approximate polynomial is x square minus x plus 5. Next, second question, which of the following suitable fixed point iteration for solving the equation cos x minus x equals to 0? 1. xn plus 1 equal to cos xn, xn plus 1 equal to cos inverse xn, xn plus 1 equal to xn plus tan xn. The option, correct option is 1. For 1 is the correct option, so xn plus 1 equal to cos xn. Here, let fx equal to cos x minus x and this equals to 0. We can write this x equal to cos x, this equals to phi 1x, say, and alternatively, we can write cos x equals to x, and so x equal to cos inverse x. This cos inverse x is called phi 2x, second function, either phi 1x or phi 2x. Now, for fixed point iteration, we know that modulus value of phi 1 dash x or phi 2 dash x modulus value of this, which is less than 1 in the interval 0.6 less than x less than 0.8, because here function f 0.4 is positive and f 0.6 is positive and f 0.8 is negative. So here the simple real root lies in the interval, open interval 0.6 and 0.8. So in this interval, condition convergence for fixed point iteration, this modulus of phi dash x is less than 1 in this interval. So we can find phi 1 dash x, modulus of phi 1 dash x is less than 1 in this interval, and modulus of phi 2 dash x is this 1 by root over 1 minus x square, which is greater than 1 in this. So we have the exact function, this x equal to cos x is the exact function for appropriate function for this fixed point iteration. And option 3 is option 3, xn plus 1 equal to xn plus 10 xn, is obviously rejected because we cannot find any form uh, mm, of this type. Next question. C. The process of constructing a sequence of vectors and obtaining the solution of a system using specified accuracy is called elimination, reduction, iteration, and Rapson method. Here, correct option is 3. A process of constructing sequence of vectors and obtaining the solution of system using the specified accuracy is called iteration. Because elimination and reduction are not sequential process. Here option 1 elimination and option 2 reduction is not sequential process. And Rapson method is a method which is employed for finding the roots of an equation through some different procedure. So correct option is 3, is the iteration process. Next question D. Let fx equals to x to the power 5 plus x to the power 4 minus 3. How many steps of the bisection method are required to approximate the root within the 10 to the power minus 100? Correct option is 2. Now we know that this modulus of xn minus alpha is less than or equal to b minus a by 2 to the power n. For this bisection method, this the b alpha is the exact root, and b and a is the interval within which the root lies, a comma b, and also b minus a to the power n for in the iteration is less than equal to epsilon. Epsilon is the error at the nth step. So obviously 2 to the power n is greater than equal to b minus a by epsilon, and obviously taking logarithm to the base e, n log 2 greater than equal to log of b minus a by epsilon. And then n greater than equal to log of b minus a by epsilon by log of 2. Here f of 1, here fx equal to x to the power 5 plus x to the power 4 minus 3, so f of 1 equal to minus 1, and put x equal to 2, we get f of 2 equal to this positive and f of 1 is negative. So the real root lies between 1 and 2, so here b equal to 2 and a equal to 1, and epsilon equal to 1 by 10 to the power 100, because the root error is 10 to the power minus 100, so epsilon is 1 by 10 to the power 100 is given. And putting all these in the equation in the inequality 1, n greater than equal to log of 2 minus 1 by epsilon 1 by 10 to the power 100 log 2, we get this log 10 100 into log 10 10 to the base 2, and after calculating log 10 to the base 2, and we get 3 into 3.32 into 9 into 10 100, so 332.9. So n is a positive integer which is greater than equal to this, so obviously the least value of n is 333. Next question E. If fx has an isolated 0 of multiplicity 3 at x equal to xi, and the iteration xn plus 1 equal to xn minus 3 fxn by f dash xn converges to xi, then the rate of convergence is, correct option is 3, quadratic. Because here we know alpha is a multiple root here for the equation fx equals to 0 with multiplicity m, and then fx equals to x minus alpha whole to the power m into gx, where g alpha not equal to 0. And the modified Newton-Raphson iteration is given by xn plus 1 equal to xn minus m into fxn by f dash xn. And xn is the nth approximation of the exact root alpha. Now we choose the Newton's iteration function phi x as, and phi x equals to this x minus m into fx by f dash x. is called phi x. Then the iteration formula gives, so this iteration formula xn equals to xn plus 1 equals to phi xn. Now phi x equals to so x minus m into fx, value of fx is x minus alpha to the power m into gx, put this, and f dash x, obviously this expression m into x minus alpha to the power m minus 1 gx plus x minus alpha to the power m g dash x. And so dividing both numerator and denominator of the second term of the right hand side by x minus alpha to the power m minus 1, and hence we get x minus m into x minus alpha gx by m into gx plus x minus alpha g dash x. Now phi alpha equals to alpha minus m is alpha minus alpha, obviously 0, so this second term is equal to 0, so we get phi alpha equal to alpha. Also phi dash x equals to 1 minus m into gx by m gx plus x minus alpha g dash x minus x minus alpha ddx of this expression. So phi dash alpha equals to 1 minus mg alpha by mg alpha plus 0. This is x minus alpha, so put alpha minus alpha 0, and obviously alpha minus alpha 0, so this term also 0. So we get m 1 minus 1, this equals to 0. So phi dash alpha equal to 0. Let epsilon n equals to alpha minus xn is the error term of the nth approximation. Then epsilon n plus 1 equal to alpha minus xn plus 1. And this alpha is equal to phi alpha, because phi alpha equal to alpha, and xn plus 1 equals to phi xn is the iteration formula of phi xn plus 1 equal to phi xn. So we get phi alpha minus phi xn equals to this. Because of Taylor's series expansion, phi alpha minus epsilon n that is equal to phi xn, this is equal to phi alpha plus xn minus alpha, that is epsilon n phi dash alpha plus xn minus alpha whole square, that is epsilon square by factorial 2 phi double dash xi n, where xi n is the lies between this minimum of xn alpha and maximum of xn alpha. This is xi n. So we can write this phi alpha minus phi xn is equal to this. So we put this epsilon n plus 1 equal to this. Now epsilon n plus 1 equals to 0, minus half of epsilon n square, xn minus alpha equal to epsilon n square into phi double dash xi n. Because phi dash alpha equals to 0, already we get this result, phi dash alpha equals to 0 here. So put this result. So we get epsilon n, modulus of epsilon n by modulus of epsilon n square equal to modulus is, so is positive sign, 1 by half phi double dash alpha. As n tends to infinity, xn tends to alpha and xi n tends to alpha by Sandwich theorem. And the order of convergence of this method, obviously introduction method, is 2, is quadratic. That is quadratic because the definition of order of convergence is modulus of epsilon plus 1 by modulus of epsilon to the power p tends to lambda asymptotic error, asymptotic value, this lambda as n tends to infinity, where lambda is greater than 0, and for order of convergence is p. So here order of convergence is 2, quadratic. If phi dash alpha not equal to 0, then Newton's method will converge linearly, that is order of convergence 1. And from this expression, this not equal to phi dash alpha not equal to 0, then we get this result. So this is then epsilon plus 1 by mod of epsilon is equal to half is equal to phi alpha. Next question. If Ex with the relative error in computation of the approximate value capital X positive capital X, the relative error while computing the value of x to the power 1 by 10 is ex 1 by 10, 10 ex by 10, and also ex. Let y equal to x to the power 1 by 10, x is positive. Then obviously log y to the base e equals to 1 by 10 log x to the base e, means 1 by y delta y equals to 1 by 10 delta x by x. Obviously 1 by y and derivative delta y equal to 1 by n delta x by x. So relative error in y, by definition delta y by y. So this equals to 1 by 10 delta x by x. Now delta x by x is the ex, because the ex is the relative error in computation of the approximate value of x. So ex is the relative error. So value of ex is delta x by x. So we put this delta x by ex. So relative error in y, that is ey, equals to delta y by y, that is equal to 1 by 10 ex. So correct answer is 3. Next question. G. The 2-point central difference formula for f dash x where h is positive is this. Correct option is 2. Fx plus h minus fx minus hb whole divided by 2h. Now f of x plus y, f of x plus h equals to fx plus h into f dash x plus h squared by 2 factorial 2 f double dash x plus h cube by factorial 3 h triple dash xi is the Taylor's expansion series. And if x minus h equals to fx minus h f dash x plus h squared factorial 2 f double dash x minus h cube by factorial 3 f triple dash xi dash, another xi dash value. And subtracting this, f of x plus h minus fx, fx plus h minus fx minus h. So we get cancel this term. So 2 f, subtracting this, so 2 fx cancel, so f 2h into f dash x, and this minus cancel, and this order of h2. So f dash x equals to fx plus h minus fx minus h by 2h, and this is the 2-point central difference formula for f dash x. H, question H, the sum of coefficients of Simpson's 3/8 rule for evaluating integration 1 to 10 fx dx is, the correct option is 3. Because we know to find the numerical integration a to b fx dx, we use n plus 1 point Newton-Cotes quadrature formula, closed type. It is I Newton-Cotes equals to b minus a summation I equal to 0 to n capital Ki n fxi is the formula, Newton-Cotes formula, where the Cotes coefficients Ki n and I runs from 0, 1 to n are the independent of the problem. For n equal to 3, we get a is equal to b minus a by 3, and x0 equal to a, xi equal to x0 plus I equal to 1, 2, 3. And for Simpson's 3/8 rule, inc equals to b minus a k03 fx0 plus k13 fx1 plus k23 fx2 plus k33 fx3, where k03 equals to 1 by 8 equals to k33, and k13 equal to 3 by 8 equal to k23. And sum of all these Newton's coefficients, I equal to 0 to 3, Kin equals to 1 by 8 plus this equals to 1. So summation Ki n I equal to 0 to n 1 always. Next question. We consider dy dx equal to fx for initial condition yx0 equal to y0. Simpson 1/3 rule is equivalent to option 3, fourth order Runge-Kutta method. For Simpson 1/3 rule, we evaluate the function at the right endpoint and left endpoint at the middle point. and then take a weighted average of those values, and we can get numerical approximation for integrals with a very few number of points. The analog of Simpson's one-third rule for differential equation is called the Runge-Kutta fourth order method. Here the Runge-Kutta fourth order method scheme yi plus 1 equal to yi plus h by 6 k1 plus 2 k2 plus 2 k3 plus k4, where k1 equal to f xi yi, which is the slope of the left side of the interval, k2 f xi plus h by 2 comma yi plus h k1 by 2, slope at the middle of the interval, and k3 equal to f of xi plus h by 2 yi plus h k2 by 2, and the corrected slope of the middle of the interval, and k4 is the f of xi plus h yi plus h k3, slope of the right side of the interval. Like Simpson's rule, it is a fourth order method and error to proportional to h to the power 4. Now, fx equals to y dash x, that is dy dx equals to fx. And so k1 equal to fxi, k2 equal to f of xi plus h, and k3 equal to f of xi plus h by 2, k4 equal to f of xi plus h. Here we get yi plus 1 equal to yi plus h by 6, k1 plus 2k2 plus 2k3 plus 2k4, sorry, k4, and we get value for this k1 equal to fxi and 2 f of xi plus h, 2 f of xi plus h by 2, and this, so after simplification we get f of xi 4 into f of xi plus h by 2, f of xi plus h. Now obviously this formula is the identical with the Simpson's 3-point Simpson's one-third rule, and so the Runge-Kutta fourth order method is analog to the Simpson one-third rule. And last question, J, the Gauss-Jacobi's iteration method for the set of equation x1 plus 3 ax1 equal to 7, ax1 plus x2 equal to 4, and a not equal to plus minus 1 by root 3 will surely converge for the correct option 3, modulus of a is less than 1 by root 3. Here the coefficient matrix of the system 1, 3, a1, and this x1, x2, and corresponding right hand side vector 7, 4 column vector. And coefficient matrix Gauss-Jacobi iteration or Gauss-Seidel iteration converges if and only the spectral radius of the iteration matrix G is strictly less than 1. Here G is the some iteration matrix is G, rho G is less than 1. That is maximum of modulus of lambda is the eigenvalue is less than 1. Where G iteration matrix equals to D inverse L plus U, where D inverse equal to 1, 0, 0, 1, and L equal to 0, 0, A 0, lower triangular matrix, and U is the upper triangular matrix is this. From this theory, G equal to D inverse L plus U, and hence G equals to 0, 3, A 0, and the eigenvalues are of G plus minus root 3A. So spectral radius is less than 1, so root 3 modulus of A is less than 1, that is modulus A less than 1 by root 3. Alternatively, we can find this theorem from this theorem, this for system ax plus by plus equal to p and cx plus dy equal to q, a necessary and sufficient condition for convergence for Jacobian Gauss-Seidel iteration method, mod of BC is less than mod of AD. Here is the coefficient matrix, and we can write A as D plus L plus U, where D is A0, 0D, and L is the lower triangular matrix 0, 0, C0, and U is the upper triangular matrix 0B, 0, 0. And D inverse equals to 1 by AD into D0, 0A. The iteration matrix G equal to D inverse L plus U. So obviously we get G equals to this. And the characteristic equation of this G equal to this, and so lambda square equal to plus minus BC by AD. And the spectral radius of this rho G is less than 1. That is modulus value of BC by AD is less than 1. So modulus value of BC is less than modulus value of AD. This is the theorem. For necessary sufficient condition for Gauss-Jacobi or Gauss-Seidel iteration method is modulus of BC. Modulus of BC is less than modulus of AD, and we can use this result in this problem for this here. This 1 into 1, 3a into a, b into c, 3a square is less than 1. That is, a square is less than 1 by 3. So modulus of a is less than 1 by root 3. And extra note for this, for a system ax equals to b, where a is the coefficient matrix a11, a12, a21, a22, and capital A is the coefficient matrix, we can write d plus a plus u, where d is this, L is the lower rectangular matrix, U is this. And the iteration for Gauss-Jacobi is given by xk plus 1 iteration equals to d inverse b minus this b for right hand vector b minus L plus u x k iteration. And we can write this. The necessary sufficient condition for convergence of any iterative method is spectral radius of this iteration matrix d inverse L plus u is less than 1. The spectral radius of iteration matrix d inverse L plus u is less than 1, and the maximum of the absolute eigenvalues is called the spectral radius of the square matrix. Note that sufficient condition, not necessary condition, for the method of convergence is that A is strictly diagonally dominant. That is, summation I equals to 1 to n, where I not equal to j, modulus of aij is less than modulus of aii. That is, Jacobi method sometimes converge even if this condition will not satisfy. And so we can use this theorem for simplification, for application of this problem, incidence sufficient condition by this, and completes this MCQ 2021 CC 14. Thank you.